things I did judging a high school science fair, and somebody did the bed of nails, but actually did not go through the calculations. I didn't realize that until after I'd gotten on it. It didn't puncture me. I was fine, but I should have asked that question before I got on it. Of did you do the calculations to figure out the spacing of the nails?
And he goes, huh?
Pretty much afterwards. So it deals with the final force that's being applied and the area over which it is being applied. In other words, force divided by area is just pressure. So if I take on my equation right here and multiply both sides by the volume, on the left-hand side I get pressure times volume, and on the right-hand side I get 3 N M V squared. And I know from the ideal gas law, using the physics version of it, that's equal to N kBT is equal to 3 in number of particles times the mass times the average velocity squared. N cancels out. And that's on the form I want.
So KBT equals 3m velocity average squared?
Yeah, I feel like I've got a 3. That 3 is in the wrong spot. Oh, God. Some days I think I'm losing it. Some days I'm thinking 8 o'clock in the morning is too early. And then I think back over my life and think, I've been doing this a long time. This is correct here. That's V squared. And therefore, Vx squared equals, if V squared is equal to 3Vx squared, Vx squared is so that should be a third.
So you had it right in the beginning.
Yeah. No, let's do it slightly better than that. No. All right. So this is now simplified into KBT is equal to 1/3 mv squared. So we talked about mv squared already and where that generally shows up, and that was kinetic energy, but kinetic energy is 1/2 mv squared, not 1/3 mv squared. So what I'm going to do is I'm going to multiply by 2/2. So I have 2/3 times 1/2 mv squared is equal to kBT. I now have a kinetic energy thing here. That's the average kinetic energy. Multiply by 3/2, and so I have my average kinetic energy is equal to 3/2 Boltzmann's constant times the temperature. So when you are looking at as particles are moving around in a box, or if we're talking about the particles in a table, that if I know the temperature of it, I can predict what the average kinetic energy is. Let's just do a quick run through there. And hope that I've actually written down what Boltzmann's constant is in a convenient place. Some more formal derivation.
I feel like that binder holds the mysteries of the world in it.
Say it again?
I feel like the binder, that binder,
And it is chaotic, so yes, that might be right. All right, fun with Boltzmann's constant. I'll actually use a number here.
and this is the thermodynamics chapter.
This is thermodynamics, yes. There we go. So, let's assume that the temperature in this room is about 20 degrees Celsius.
We don't use Fahrenheit.
You can if you wish. Good luck converting it to Rankine. If I want to convert this to Kelvin, because that capital T is in absolute terms, how do you get from degrees Celsius to Kelvin?
Multiply by something.
No.
Don't you add
Yes.
270? Something around
Yeah, so close. You add 273.15. And so we get 293.15 Kelvin. It is not degrees Kelvin, it's just Kelvin. So 3/2 times Boltzmann's constant, 1.38 times 10 to the negative 23rd. So 1.38 times 10 to the negative 23rd joules per Kelvin times the temperature, 293.15, equals the average kinetic energy. Well, what's the average mass of a molecule in air?
Negligible.
What'd you say?
Negligible.
So the speed is infinite.
Oh, well, I see what you're saying.
Yeah, we're dealing with, oh, wait. Nope, not what I wanted. That's the one I wanted, all right. So we are roughly 78% nitrogen N2 and 21% O2. It's only 99%, but the rest of it I'm not gonna worry about. This is N2. I have 2 nitrogen atoms. We go over to the periodic table. And I see this 14.00674. That is the number of grams in 1 mole of nitrogen. So 14.0674. So 14.00674 grams per mole. And that's 0.78%. Plus 0.21 times 2. And I'm multiplying times 2 because it's N2, not just N. O2, 15.9994. 20.21 times 2 times 15.9994 divided by 0.99. This will give the atomic mass. So, would someone be kind enough to do that calculation? I guess grams per mole, if you're gonna try
Thank you.
It's gotta be something between 28 and 32.
28.859.
Units?
The grams?
Grams per mole.
Yeah.
All right, so if I take 6.02 times 10 to the 23rd air molecules from the air, that's the amount of mass it has. So I can figure out what the mass is per particle by just converting this. So first, let's put it in kilograms, just so that we're in SI units. So 0.02889 kilograms. And then a mole is 6.02 times 10 to the 23rd particles. So if you take that divided by this, we get a very tiny number, but again, we are talking about nitrogen and oxygen molecules. What do we get the mass per particle then?
I got 4.79385 times 10 over power of negative 25.
25. Anyone else get the same thing? That doesn't seem right.
I got the same 4.79, but times 10 to the 20th.
20th?
Oh, wait.
I think you got a parenthesis in the wrong spot. Tristan?
I had the same 4.79, but to the negative 26.
Negative 26 makes more sense.
I got that.
Because I got negative 23 right here. Move this over 2 places, I got a negative 2, so that gets me negative 25, and then I've got basically 2 divided by 6, which is under 1, so that should be a negative 26 here. Kilograms. So I now have the mass of a particle. So back over here. This whole thing is equal to 1/2 times that mass. 4.79 times 10 to the negative 26 v squared. And so we can figure out the speed of these particles that are zipping around this room.
Times 10 to the negative 26.
Yes. Thought you were giving me an answer. Got excited?
3.
You got an EE button there? It's on the calculator, but
Silver edition.
Yes.
E, but. Yes, right here.
all right. So you would type in the 1.38. So I'm just going forward. All right. Yeah. 1.38. Then EE. And then
What you said? Just E?
when you hit,
This one?
no, that's not it.
No, okay, delete it. Oh, this one, E.
All right. Yeah. All right. Then type in -23. Negative. Oh, you got it. Negative. All right. There you go.
Times 193. 1.5.
And so, Ali, when you typed it in, did you do 10 times 10 EE?
I added that.
Yeah, so you can multiply it by an extra there. The EE automatically has the times 10 to the.
Okay. Thank you.
At least that's the, for people who are off by a factor of 10, that's the most common mistake I've seen. Times 10 to the negative 22nd, or 26th. 26th.
And then we take that sign and divide by that sign.
Yeah. What'd you get for this side before?
I got 6.06205 e to the negative 21st. Dividing such by that. That's a big number. Square root that. Okay, so my final answer is 503.358.
What are the units?
Meters per second.
So on average, playing a little bit fast blues for those who've done statistics classes or hardcore statistics. The particles around us are zipping around a little over 500 meters a second. Smacking into us.
Why don't they go through us? Oh, well, you finish and then I'll answer.
Tough skin.
Oh, that's good.
I mean, it does hit. I mean, they may not, we may be assuming that they don't interact with each other, but they do interact with walls and people and stuff like that. It's what keeps us from basically having our blood boil. Or, if you believe the movie Outland, keep us from exploding. But I think that's not true. It's not as dramatic. There have been a couple of accidents while the Army was doing low pressure experiments where people were exposed to much lower pressures than intended or for longer than intended. They did not explode. All right. Questions to hear? All right, in the limited time remaining, I want to talk about fluids. A lot of physics, thermodynamics is statistically based. I mean, I sort of hinted at it here when I talked about the average of V squared. But if you get into hardcore physics, thermodynamics, that's just a lot of averages, and all the rules are basically, statistically speaking.
What does that mean?
That means that typically temperature or heat will flow, energy will flow from a hot object to a cold object.
Right.
Statistically speaking, because it is possible for it to flow the other way. It is possible for a lake to freeze in 100-degree weather. Degrees Celsius or degrees Fahrenheit, I don't care which one. It definitely would freeze in 0 Kelvin.
What?
But the odds are against it. If I throw a ball against the wall, there is a probability the ball will go through. Just the odds are against it. I mean, not make a hole in the wall, it would just suddenly materialize on the other side of the wall. And that, which is actually the basis of the scanning electron microscopes. You shoot electrons at targets and occasionally it will go through. Mysteriously appear on the other side. All right, so density. What's the formula for density?
MV squared, no. Is it mass over volume?
Yep, mass over volume. This is the letter rho, Greek letter rho. If you're looking at a Cyrillic alphabet, it's very similar to the rho. In the Cyrillic alphabet, this makes the R sound.
Why can't we just get
All right, so imagine I've got a container here with a liquid that I'm just gonna arbitrarily divide in half. So I have sort of the top half and the bottom half here. What I want to do is